Hi everyone, today we will be talking about creational design patterns. So, without further ado, let's get started with the first one. Most common way of categorizing design patterns is by usage of those patterns, and it is divided into three main categories: creational, structural, and behavioral. Singleton belongs to creational design patterns. One of the most frequently asked questions related to design patterns at any programming interview is to explain the singleton pattern. It is one of the simplest, if not the simplest design pattern. However, it comes with certain implementation concerns that often come up as follow-up questions. Its purpose is to make sure that only one object of a class is being created in whole application, which is where the name singleton comes from. Runtime from java.lang and desktop from java.awt are well-known Java classes implemented as singletons. In real-world apps, we use singleton for caches, loggers, and database connections. Here is a graph demonstrating how singleton can be used in real-world scenario, where we have multiple observatoriums and a single sky that has a list of stars or their names. By making sky a singleton class, all observatoriums will share only one instance of the sky class. After talking about the usage of singleton design pattern with your interviewer, one of the most common follow-up questions is how you would implement it. We have displayed one way of making class a singleton. We have implemented previously mentioned sky class. First thing to notice is that we have a private static variable called instance of type sky. Next thing is making the constructor of sky class private so that nobody can instantiate objects outside of the sky class. Last important part is adding the public static getter of that instance variable so that it can be accessed outside. We have chosen to lazily initialize instance variable in this getter method, but we could have also initialized it in constructor, static block, or when defining it. All of these options are valid. However, by using the lazy initialization, you optimize your application for the situation when no one actually calls that getter method. It is also important to say that the mentioned getter method has to be synchronized. Otherwise, it could happen that more than one thread is calling it and thus creating multiple objects of the sky class, which beats the sole purpose of this design pattern.
Factory belongs to creational design patterns. Factory design pattern is used when we want to decouple creation of subclasses objects from client code. To apply this pattern, we need to have superclass that has multiple subclasses whose objects we want to create based on some input. This design pattern is also referred to as a virtual constructor. By using factory design pattern, it is a lot easier to extend set of current subclasses by only adding them in one place instead of making changes all over the code where these objects would be created otherwise. GetInstance method from the Java util calendar is implemented as a factory design pattern. Method that is creating the objects in factory class is often called factory method, which is another name of this design pattern. Here is a graph demonstrating how factory can be used in a real-world scenario where you have different shapes and a single factory class that is creating specific shapes based on some input from the client. If we would want to add another shape, let's say triangle, we would only need to extend the method in the factory class where these objects are created. Bear in mind that for the shape type, you can use interface, abstract class, or a regular class. In our implementation of this use case, we have chosen to use interface for the shape type, and as you can see, we have one abstract method called draw. Here, We have also shown a circle class implementing the shape interface and its method draw. Implementation of rectangle and square classes are almost the same with a slight difference in the message logged. Here is the factory class with its factory method called createShape. We clearly see that return type of this method is shape, and that based on the shape type parameter we decide which concrete object we will instantiate it. Usage of factory method is currently being displayed. If you look at the console output, you will notice that different messages have been logged corresponding to the shape type argument that we have passed to the factory method.
Abstract factory belongs to creational design patterns. Similarly to factory design pattern, which we have already covered, abstract factory pattern is used to decouple creation of family objects from client code. Main difference from factory pattern is that it has a set of factory classes, and that's why it's also known as factory of factories. By simply changing the factory that we are using, we can substitute a whole family of classes in the application. One of the biggest disadvantages of this design pattern is supporting new set of classes, which would require changes in the factory layer as well as adding a completely new factory. Let's have a look at the example demonstrating the usage of an abstract factory design pattern. We have a shape and its subclasses empty circle, empty square, filled square, and filled circle. Now let's have a look at the layer of factories. First, we have an abstract factory and its implementations, empty factory and filled factory. Empty factory creates empty shapes, while filled factory is used to create filled shapes, as we can see. A client comes and wants to create some of these objects, but he is not aware of any of the specific factories nor concrete classes of shapes. Only thing that he can do is to provide some input on what kind of shapes he wants. Factory generator comes in play to determine which of the factories should be created, and then the corresponding factory will create concrete object that client requests. Now, let's go through the implementation of this example. As for the factory design pattern example, we have chosen to use interface for the shape type, and as you can see, we have one abstract method called draw. Here, we have also shown a filled square class implementing the shape interface and its method draw. Implementation of other shape subclasses are almost the same, with a slight difference in the message logged. Empty shaped factory and filled shape factory have almost identical implementation, but the key difference is that they are creating two different families of objects. Depending on the shape type parameter, they will either create a specific type of circle or square. Here we have displayed implementation of the factory generator and how the proper specific factory is being chosen based on the factory type parameter. Execution of this use case is currently being displayed. If you look at the console output, you will notice that different messages have been logged corresponding to the factory type as well as shape type argument that we are passing to our factory layer.
Builder belongs to creational design patterns. Creating complex objects can be error-prone, and that's when the builder design pattern kicks in to solve that problem. With large number of fields in a class, it would be a nightmare to provide all combination of constructors if some of them would be optional. It is also very easy to mix up the ordering of the constructor arguments. Builder design pattern takes the responsibility of creating such objects by providing an interface for configuring any combination of object fields. Given the broad usage of this design pattern, engineers have developed some tools for auto-generating builder classes by using the appropriate annotations. One such framework is Lombok. String builder and string buffer from Java Lang package are well-known classes of builder design pattern. To better understand why and how we use builder pattern, we will first demonstrate how the following example would look like without it. We have a meal class that can have multiple dishes in it, like an appetizer, main dish, drink, salad, and dessert. We have only shown few examples of constructors, but you can see for yourself that the list is not complete. Now, let's have a look at how the client code would look like. We clearly see that we need to know what kind of constructors does meal class supports, and with that create appropriate objects. But if we take a closer look at the main dish with an appetizer object and how it is created, and go back to the implementation of meal class, we will notice that we have mixed up main dish and appetizer argument, which is a common mistake when creating complex objects. Let's have a look at the example demonstrating the usage of a builder pattern. We have a client that wants to order a meal with specific dishes. That's when the builder kicks in and starts preparing the meal. Client wants main dish, an appetizer, and then a drink in his meal. Once the meal is being prepared, client can just start consuming it. Now, let's go to the implementation of this example. All of the meal and builder code is placed in a single class where builder is an inner static class. They both have same class fields. Meal will have a private constructor which receives an object of builder type. Apart from the constructor, it will also have a static method for getting an instance of the builder class. Builder will have methods to configure different parts of the meal, and all those methods will return the current instance of the builder, which allows chaining of builder method calls. Last thing is the build method that actually creates a meal object which we previously configured through the builder class. Looking at the client code we kinda already had, we see that this is much cleaner and less error prone while accomplish the same thing.
Prototype belongs to creational design patterns. This design pattern is used to make either deep or shallow copies of existing objects in cases where creating new can be costly. Prototype class offers a clone method that deals with copying all of the original object attributes so that client code does not need to be aware of the prototype class structure. For immutable types of attributes, we use shallow copying as those could be shared among different instances. Let's have a look at the example demonstrating the usage of a prototype design pattern. We have a client that wants to create a robot with certain robot parts. Before he starts playing with that robot, client would like to make a clone out of it. Once those parts are replicated, he will assemble them into a robot clone. Client can now start using the clone robot. Now, let's go through the implementation of this example. We have an abstract class robot part that has an ID and an abstract method getName. We have also shown one implementation of the robot part in the left arm class that returns an appropriate message. Other robot part implementations have the similar behavior with corresponding messages. Robot is a prototype class as it contains the clone method that will create a new list of robot parts, and for each part in the existing list, create a deep copy and add it to the new list. As for the Wi-Fi password field, we just pass the same reference as string is immutable, making it a shallow copy. Here we have shown the client code that uses the capability of robot cloning. We create a robot with a head, left arm, and right leg. Once we do that, we call the clone method, which returns a clone object. You can see in the console output that by logging the robot parts from both original and cloned robot, we get the same types and number of robot parts. However, since we used a deep copy, they all have different IDs. Thanks for watching this video. If you liked it and you would like to see more content of this type, please click the subscribe button and turn on the notification bell. If you have any questions, post them in the comment section below and we will try to respond as soon as possible. Till next time, goodbye.